Okay, good afternoon. Let's start. Um, so last time, I had just to recap. So we had gone over sampling methods and particular compressive sampling, and again, kind of a key takeaway there was that if you know more about the signal, or if you wish to do things other than
I have a question about the compressive sampling.
Sure.
So is that all done in software?
You can do it either way. So there are you can have the A to D converter do the random sampling for you. So there are chips like that, as well as you can do it in the driver which is driving the A to D converter,
Right.
or you can do it entirely on the digital side. That is, your A to D converter is still sampling at Nyquist rate, and you are just subsampling from that.
Right.
Okay, so in which case it's entirely software.
Yeah, my confusion was because like normally with the ADC, like you have to supply like a clock, you know, and like that's kind of like its
Right.
reference to sample. So like if you're sampling at kind of like arbitrary times.
So A to D converters, you use one of two ways. One is that every time you need a sample, you go to the A to D, say, read a sample, right? And if you wish to do it periodically, you can do it through some a timer on your chip, for example, right, which fires, and then an interrupt handler. You do it. But also, A to D converters typically allow you to simply tell them that sample at this rate. And then internally, the A to D converter then has a timer, basically, and it samples, and then every time it has a sample, it just puts it into a buffer and raises an interrupt or something like that, right? So in which case, you don't have to maintain the timer. So, but they're basically equivalent. It's just that how you're structuring it. But also, quite common is simply for you to do it in software. When it comes to compressive sampling, since we are sampling at random moments, so vanilla chips obviously don't have them. So you are going to arrange somehow that there is a timer tick, but then on that timer tick, you're going to do a lookup at that matrix and say, okay, shall I sample or not, for example. But there are also chips which were designed specifically for this paradigm. So I mentioned that there were some large funded research programs in this space, so those did create chips. In fact, the name for those chips were analog to information converters as opposed to ADC, AIC. And I recall like a group at Caltech, for example, had created all the way down to a silicon there. But you will not find those kind of chips in the commercial catalog. So commercial chips, if you wish to do it, you basically have to arrange that under some software control, you are doing that random sampling. Okay. The flip side, the decoding, that computation is actually quite intense because you're basically solving a optimization problem there, and for that also people have created hardware support because it's computationally kind of intense. But that's more in the sense of accelerating that computation somehow. Okay. So so sort of two key insights there, which is if you know more about the signal, or if you wish to do things other than reconstruct, then you can be smarter about sampling. And the other approach we had talked about was adaptive sampling, which is basically the insight that I could be, if I see the signal is changing less, perhaps I should take a larger step in time or space, as the case may be. And yeah, I guess the final bit was that back to compressive sampling, that there is a universal way of doing compressive sampling, which was that random matrix approach, which is basically, if you think about matrix as nothing but a linear transform, all transforms do is to map it into a different space. So we are basically mapping it into some space, and it turns out kind of that these random matrices basically preserve the information, but let you sample it in that nice manner so that even with fewer samples, you are able to recover the original signal. Okay. So that was on the sampling side, and then we had started on the sensing side, and kind of distinction. The task of sensing, you could view it as the task of making an inference about the state of the physical world or the platform itself. So the latter being the external sensing and external versus internal sampling, but eventually it's about some sort of a state estimation. And so, for example, I mean, what you measure are waveforms corresponding to some physical signal. To convert them into digital, you somehow convert them into voltage or current, which is what your A to D converter is going to sample. And then you have a number, but that number corresponds to that physical quantity. And then you rely on some sort of a physical model or some other data-driven model to kind of relate it back to something of interest, right? So for example, some of you are, well, at least one project is looking at heart rate variability, which relates to physiological stress. And that has come from, that insight has come from people who study biological systems, namely sort of people, doctors and all, which basically show that there is an association, that there exists some pathway so that physiological stress, which is ultimately in terms of some chemicals being secreted in brain, that also expresses itself through the body's body chemistry and electrophysiology into a variation that you can observe in the heart rate. And likewise, things like sweating and all kind of relate to that as well. So you could imagine, given a heart rate variability, to make an inference about the stress, one could go around doing it many different ways. One is maybe we have sufficient insight about the underlying sort of biological circuit, if you may. So the one where deep inside there is some physiological stress, and through body's sort of biology and it's expressing itself as HRV, heart rate variability. And if we know that forward model, then it's kind of like an inverse problem, right? Given the heart rate variability, I want to make an inference about what the underlying stress is. Now, usually that information is, that kind of knowledge we don't have. So then the task becomes that, okay, so if I suspect such a pathway exists, that there is such a dependence between that state of interest and what I'm observing, but then maybe I can learn a data-driven model. And the way you learn a data-driven model is that maybe you will have some way of getting the ground truth, as we in engineering call it, that is some other sensor which is telling me the reality. So for example, in case of stress, it could be the reading of that particular chemical, for example, or maybe there exists some other sensor which you trust. So it's kind of interesting, but in engineering we use the term ground truth quite often, but if you talk to people in sciences, they call it as a gold standard. So the idea is that perhaps already exists some sensor which everyone trusts, and I have this hypothesis that, maybe HRV relates to stress, for example, let's say. And then what I can do is I can use the reading of the gold standard sensor or the ground truth as the reality, and then kind of train a machine learning model. So corresponding to that. So we are going to see that, but it's ultimately about making an inference about that hidden state, right? And very rarely do you have a situation that your sensor directly gives you a number corresponding to that hidden state. It's basically through some complicated function which reflects the physics, chemistry, biology of the system. So so the example towards the end that I started going towards was activity in our spaces, human activity. So whether someone is walking or is in REM sleep or is happy or is eating, there's no such thing as a sensor for these things. These are inferences which we can make out of other sensors, out of physical signatures. So you can think of deep down, when the system, humans, world is in that state, then there are signatures of this being emitted in various observable traits, observable signals, right? Sound, light, stuff like that. And by hearing those, by listening to those signals, I can then apply either a model inversion or some machine learning algorithm to kind of make an inference about the underlying state. So for activity detection, very broadly, people kind of pursue approaches which fall into a couple of different categories: sensors in the environment, and the other one is sensors on the person. Okay, so you can either instrument the environment or you can instrument the individual. So sensors in the environment could kind of a laundry list of them out there, but each one of them captures some signature of human activity. So PIR sensors are basically those motion sensors that you see in home security systems. So they basically capture the thermal signature. Magnetic door window. So essentially, human, as we engage in activities, we kind of open doors, windows, stuff like that. So again, those are capturing stuff. Temperature, light, humidity, all of these things reflect vibration, pressure, RFID, camera, kind of there's a long list. Electric meter, I mentioned last time around that as we do things in our spaces, there are signatures of it on in the energy being consumed from the electric utility, or water being consumed, or gas being consumed. So you can monitor even things at the meter to sort of do that. So lots of work in these kind of things. Like people have shown that you can make lots of detailed inferences about what's happening in a building or a household by simply monitoring that central point. Lots of things can be inferred from vibrations of the floor, things like that. People do things like instrument furniture and sort of all these sort of things. Most powerful of these perhaps is the camera, simply because it can observe stuff. But the problem is a lot of time things are occluded or are inside whatever closets and drawers and stuff like that. So there are limits even to the camera. But broad philosophy, sensors in the environment, and then sensors in the body. When it comes to our own state, sort of we move around, so therefore any sensor which is on our body and which captures the motion is revealing of our activities. So accelerometer, gyroscope, magnetometers, these are collectively called as IMUs. So sometimes you will see things like 9 DOF inertial sensor. So 9 degree of freedom basically refers to the fact that accelerometer has 3 whatever, it's 3D, gyro has 3, and magnetometer has 3. So 9 DOF refers to that. Sometimes you will see the term 10 DOF, which basically adds an additional one, which is humidity. Okay, so that's another one which, sorry, not humidity, barometer, pressure. The pressure basically is not for related to weather, but it's really the altitude that sort of gives that out. So inertial sensors are very powerful, and people, I mean, most of us have a smartphone, so at least a lot of time smartphone is coupled to your body, either in your pocket or in your hand or in your purse or things like that. So at least at those times it is picking up signatures about you, and even when it is not on you or sitting next to you, it's again potentially capturing your sound and stuff like that. So it's revealing of activity. Then we also have them in our watches nowadays. So again, most smartwatches now also have all these sensors. Plus both phones and watches have GPS, which also picks up macro motion. So inertial is a rich source, and people have done all sort of funky stuff around it, like what kind of transportation modality are you in? Okay, walking, sleeping, those kind of things. Put the phone on the bed. You can measure your sleep patterns when you go into REM sleep, stuff like that, through the stuff on the watch. Things like smoking, eating, those kind of activities which have unique sort of signatures because of the way you move the hand get picked up. People have also shown like they can infer passwords and things like that. So like phones have accelerometer, and where you type kind of induces a different signature on the inertial sensor on the phone, and then again knowing the keyboard layout and all, you can kind of infer things. Same kind of things people have done with the watches. There have been papers showing that if you're wearing a smartwatch and you're typing on a phone or a keyboard, then again knowing about the keyboard layout and all, you can make an inference about what are you typing from the inertial signature out there. So lots of these things can be inferred from the inertial side of story things. Then you have the physiological signals, which again, as these devices are becoming more sensor rich, a lot of them are being captured. So heart rate variability are pretty common on smartwatches now. So it's basically that PPG or photoplethysmograph, that LED plus optical detector that exists at the back of these devices. And between heart rate and heart rate variability, there is a lot of stuff you can infer. We talked about stress, but there are a whole bunch of other things related to fitness and stuff like that, and sort of medical problems which can be given away. Even activity, right? I mean, when we run and all, then heart rate goes up. So there are things you can capture from that. Galvanic skin response isn't there on any of these common devices, but there do exist wearables which capture galvanic skin response. Blood pressure is kind of an interesting one. So PPG, that signal which these devices are capturing, there is some work showing that you can make some estimates of the blood pressure from that, but blood pressure is much more easily doable if you have either two devices. So blood pressure kind of relates to the flow of the blood, and therefore you need to make an estimate about its transport time. So if you have two devices which are time synchronized, then you can actually measure blood pressure, but that's kind of awkward. We don't go around wearing two of these, but if we were, you could. The other way to do it is to have a closed loop. So if you notice, like ECG on my watch, for me to do ECG is I have to touch the crown with the other hand, because that's how the circuit closes. You can't do ECG just with the watch sitting on one hand. And any ECG device that you'll see of this nature, they either require you to hold it with two hands, or of course they may put lead on your body. But for the wearable, that's the model, that you kind of touch it to get that going. So ECG there are also like patches and all that people are doing. So that's revealing. EMG, EEG, and theory, people claim a lot for them. So like, what are you thinking and all? I'm sure you might have seen these TED Talks or other popular press kind of things where you have an EEG headset on you and you think and move the cursor and stuff like that. There are, to some degree, you are able to do these things, but to the extent to which they are actually revealing your mood and cognitive state is kind of unclear. But certainly brain activity at some day and age might exist. In the near term, it's the wearables that you have on your hand. Other ones which I have seen are Google Glasses type eyeglasses, except that they have a camera facing inward also. So they're tracking the movement of your pupil. And that actually is a giveaway for a lot of things. Firstly, it tells you where you are paying attention. Like right now, like if you just look at my face, that doesn't quite, I mean, I may be looking at different places, and that focus of attention is important. So some of these wearables which can examine our state in ways where another one is voice analysis. There is a fair bit of work on from the tone of one's voice to kind of make inferences about the emotive state of oneself. So these things exist. So sensors and body. So in a typical deployment, I mean, both of these play out, and I think depends upon the type of application. If you are seeking to sense something on a continual basis, then it's probably going to be an on-body sensor. So if you want to measure someone's stress state throughout the day, then it's unlikely you can instrument the world to do it. So therefore doing it on body makes more sense. On the other hand, if you have applications which have to do with whatever, an elderly person in a home, and you are trying to create some sort of assistive environment, then kind of instrumenting the environment kind of makes more sense. And so both these approaches kind of come into play. What I'm showing out here is kind of pictures from a system that Washington State Pullman, they have a project called CASAS where they deployed these things. It's kind of a old thing, so the kind of sensors you see are kind of pretty crummy looking. I mean, modern sensors are much smarter, but just a few years ago, that's how things looked like. What they did was they instrumented both individuals as well as things in the apartment. So I think they have around a dozen or so environment in that city, and in cooperation with kind of the municipality and all, they have heavily instrumented things. So all sort of activities that they do. So like, for example, hand washing, stuff like that, okay, being done. So in this particular case, what you see is there are a whole bunch of motion sensors. So here, motion sensors, there is an accelerometer, some other sensors out here, and you see kind of different kind of signatures coming up, and here these are locations. So let's see, so hand soap, so they instrumented the soap dish, power line, so they're monitoring the power line, and then kitchen closet, kitchen sink, kitchen hallway, and then they have a hot water sensor for something, okay. And for different activities, they, you kind of see that as we go around, there are signatures on multiple sensors that are going to be there. If you imagine whatever working in the kitchen or using the bathroom, then so there's going to be signatures on the electrical system, on the water system. If you have a wearable, that's going to capture something, and so to get to that state, any one of these sensors or different combination of these sensors might do the trick. Also, this is another one from the same study where they're showing sweeping activity, and kind of as the person was sort of sweeping the apartment, so you kind of see different motion sensors being triggered at different times as the person is moving through the apartment. So in general, what you're going to have is at any given point in time, there are going to be some sensors on body, and then perhaps opportunistically there are sensors in the environment, and it's the combination of the two which you could make use of. The challenge which comes is that usually none of our software environments kind of let you access all of these. So it's easy to write apps which are on your phone, which can access on-body sensors, and it's easy to have systems which are sitting in a home and accessing the sensors in the home. Stitching sensors on a person as well as the sensors around that person runs into the pragmatic problem that not all sensors are owned by the same entity, right? I mean, I may be the sensors at UCLA, I mean, like every light switch here is a motion sensor, right? That's why they turn off. Except if you want to make use of it for your purpose, you don't have access to it because it's owned by a different entity. And likewise, if UCLA wishes to do some smarter HVAC control or light control, they could, in theory, if they had data from our sensors on us, but again, they cannot either, okay? So, so one practical hurdle in a lot of these things is that sensors are owned by different entities, and just for you to discover the entirety of the set of available sensors is usually kind of hard to do. But let's imagine you're dead, so you have whatever sensors you have, then sensing is the problem of this estimation of that hidden state, right? That hidden reality. And the term that is used for this thing is latent state. So sensing is really a task of estimating that latent state. So you can think of your system as that the world, the system, the human, whatever physical or whatever natural or engineered system you're interested in, it is in some state, okay? And over time, that state is evolving. So at time step 1, it is some state S0. And you can think of the state as kind of a vector corresponding to some notion. So for example, the state of a human would be all the relevant things, including, I don't know, things like what activity he or she currently is in, what the temperature, stuff like that, all the relevant stuff. And that state is evolving. But that's not what you're getting to see. What you're getting to see in general is an indirect observation about that state, right? So what your goal then, so you can think of a sensor as some sort of entity which is applying some function over that state and is spitting that out. And your goal then, and that's what you're getting to see. With this, and kind of there are various well understood problems that kind of follow. So there's a problem of filtering, which basically says that if I give you observations from past till now, can you tell me what the state. So I have observation from time 0 to t, and I want you to tell me what that latent state is at time t. So that's the problem of filtering. There's a problem of prediction, which is basically saying, given observation from time 0 through t, tell me the state at a future time. Okay. There's a problem of smoothing, which basically says, given from 0 to t, tell me the state as it was at a prior time. So this is often useful because after you have looked at the future also, maybe you have a better estimate of the state at time t. Right? So that's the problem of smoothing. And then finally, there's a problem of inference, if you may, or most likely explanation, which is basically saying, if I give you a set of observations, then can you tell me what was the most likely pathway to the set of states? So what was the value of S0, S1, S2, S so on through ST? That's the most likely explanation. Okay, so that's in a sense, for an underlying system, that's what you are really kind of interested in doing, which is what's the most what was that sequence of states, which is the most likely explanation of the observations I had. So now, if I were to literally think of it this way, then I will always have to keep track of all the observations that I have seen thus far and kind of keep doing it in a continual manner. So that in real systems is kind of painful to do. So there are some simplifications that you end up making. So one very common simplification is that we are going to window the sensor data. So basically you're getting some sort of sensor waveforms as observations. So you window them. You would think of them in sort of some windows of time, and intuition being that the world operates with some time constants. So faster than that makes no sense. So you could assume that things were kind of stationary during that window. So you divide the raw measurements into these windows. The other thing is that kind of along the lines of what we discussed last lecture, which is these analog waveforms are probably capturing, have a whole lot of redundancy and have a whole lot of information that is perhaps even irrelevant to what I am seeking. So for example, if the only aspect of the human state, the latent state that I'm interested in is a subspace of that, like for example, the state of a human is pretty rich, but maybe all you're interested in is, is the person stressed, okay? Then a whole lot of other stuff is irrelevant. So, but all of that is showing up in that sensor waveform. So could I remove the irrelevant stuff? So that leads to the concept of features. That is, instead of working with the raw waveform, you compute statistics over them, compute various mathematical functions over them, and then based upon your knowledge of the physics of the phenomenon, or perhaps what you have seen empirically, you know that only some of those things are relevant. So like for example, if I give you the ECG signal and you're interested in stress, then it's kind of pretty well known from the medical community that heart rate variability is the primary metric of interest. And heart rate variability you compute by looking at peak to peak distance in the ECG. And therefore, if you have that, rest of the ECG waveform doesn't really matter. So the feature that we would be interested there would be that heart rate R2R interval, as it's called. So that's one simplification, right? So you split the sensor signal into windows, assuming stationarity. What's the size of the window is something you'll have to empirically determine. And then for each window, taking those waveforms, you compute the statistics that statistical features that you believe are the important one, and those are what are called as features. So essentially, a clump of waveforms over that, whatever the segments of waveforms over that windows, we kind of reduce it to a feature vector, okay, which is basically nothing but statistical estimates computed over it. Now, that's the traditional way of doing things. One of the challenges in this is that someone has to do all that physics and biology and all to kind of realize what are the relevant features, okay? So the more modern perspective or more recent perspective to this thing is that instead of human engineered features, can I bypass that whole strategy? And we'll see later kind of neural networks essentially kind of take that perspective, okay? And then another approach is that there are, if you look across kind of the literature, you will see that there are some features that keep popping up again and again. There are various features in time domain and various features in spectral domain. So what you could also do is you can start out with like a long laundry list of features, and then you prune it down based upon how they are performing. So there are methods based upon that also. Okay, so that's one aspect. So windows and features. The second part is to simplify things. Oftentimes we assume that these windows are independent. That is, I can make an independent assessment over each one of these things. Now that's not really true, because like for example, if like let's say you are examining data from an accelerometer, let's say, okay, or in those inertial sensors, then they're telling you something about my state, let's say walking, sitting, running, lying down, those kind of things. Clearly, what I'm doing unless your windows happen to be perfectly aligned with when my state changes, like when I move from walking to running or whatnot, more likely than not, you're going to have some fixed size windows. And you're probably going to pick them to be small enough so that the stationarity property holds true. So now what will happen is in a particular window, I'm sitting. Another window, I'm again sitting, more likely than not, right? So there are some transition probabilities that, like some correlations that exist window to window. So this assumption is strictly speaking not true, but in a lot of systems, that's a reasonable thing to do. So each window, we assume independence, we go ahead and make that inference, and then perhaps then you do a cleanup after that. Okay, so maybe kind of if you see like whatever, sitting, running, sitting, then you know that running was perhaps an error, right? So you can do a filtering pass at that stage. But this is another thing that you would commonly do. So you focus on making an independent inference over a window. But there are also methods which don't do this, which kind of directly attempt to solve it as a problem over time. Third thing, classification versus regression. So these are two common goals of when you are doing sort of processing sensor data. So classification basically says that my state, the thing that I'm interested in, I can view it in terms of a category. That is, it takes value from a set of values, but these values have no notion of like one being close to or far from another. So like it could be I have a camera detecting objects, and I'm just trying to say, is the object a person or a animal or a bird or whatever, right? I mean, so categories. Yeah.
It's classification.
Yeah.
I thought you said regression.
Oh, did I? Sorry, apologies. So classification is categorical, okay? Then regression is where you are trying to estimate something numerical, right? I mean, like the height of the person or weight of the person, these kind of things. And again, we encounter kind of both kind of problems in kind of real life. So next up, what kind of inference methods get used? So at the bottom is, of course, the more fashionable things at present, so neural networks, and I imagine many of you, if not all of you, probably are doing Professor Jonathan Cow's course, so that where in context of images you are seeing these, but essentially the very same neural networks and all can be applied to any inference task, including sensory data. But on the other hand, you have kind of the more traditional things. So naive Bayes, which basically applies your Bayes rule to basically reach an inference, so kind of frequency analysis based stuff. We'll see some simple examples of that. Linear classifiers, which basically use a linear function and then use sort of thresholds over it that you learn to kind of split things into categories. You can combine linear classifiers with nonlinear kernels, where basically you take the initial sensor data, apply some nonlinear kernel, and then you do the linear classification or linear regression on that. Support vector machines, which are essentially, you can think of them as a generalization of linear classifiers, where you're not talking in terms of hyperplanes. Decision trees, this is how oftentimes we do rules and all, like if, like looking at the sensor data, you can kind of create a tree-like structure where you make decisions on different dimensions. Eventually you reach the desired decision, and there are generalizations of these, like you have multiple decision trees and all. And then perceptrons were the precursor of neural networks, and then finally neural networks. Oftentimes what also happens is you use ensemble of these things. So you basically, instead of looking at the result of just one, you basically have a whole collection of such inference methods, and then you combine the results somehow. And the idea being that each different inference methods may have different failure points, and also you can think of these inference methods themselves as kind of like sensors. They're trying to sense the output given kind of the input, and they introduce their own noise of various forms. So by having an ensemble of them, oftentimes you kind of do better. But before you apply these inference methods, challenge that you also face is that the underlying sensor data that we kind of start out with are often quite messy. So you can't just compute the feature vectors, or in case of neural networks, just the data. Usually you would not feed them directly. And the reason simply is that sensors suffer from lots of issues, noise, calibration, things like that, and handling them upfront yields much better results subsequently. So the very first stage of a sensing pipeline then simply is to correcting these or trying to deal with these problems. So there are many sources of such problems that occur in real systems, various kind of noise. Sensors have given operating range. So for example, there will be min-max ranges over which it will operate, and anything outside that it will saturate or do sort of other funky things. Actuators have noise and errors. So if you're looking at an overall system, just like sensors have noise and errors, so do actuators. So all of these things sort of collectively come into your way. So usually in sensors, as part of the circuit itself, or very close to processing, very right after the A to D converter gets done, and these are referred to as signal conditioning. Just a sec, there is some text which is not showing up properly. Okay, so the values coming out of that piece of hardware, which is referred to as transducer, are often not of adequate quality. So you may want to sort of clean them up. And there are kind of many approaches to doing it, but basically it boils down to kind of a problem of filtering, as you would often refer to this. So for example, maybe you will collect multiple samples and then average them out. Or oftentimes median filtering is used a lot. The advantage of median filtering instead of simply averaging is that median filtering is more robust to outliers. Okay, so that's the benefit. Even very simple sensors can have problems. So like for example, let's say there is a button which you are trying to detect when it is being pressed, and you want to then act accordingly. The problem with is that these are mechanical things, and when the contact is not simply, oh, it was disconnected and connected, there's going to be, at the moment of contact, there's probably going to be some bouncing around. So if you look at the signal, which even a simple button will have, it will probably look like this. It will have a few transitions before it becomes stable, and then again some transitions before it goes up, before it becomes stable at its new value. And you want to filter these things away. So this is called as debouncing. So this is an example. And there are these kind of issues which sort of sensors just suffer from. These kind of button type sensors are quite common in security systems and all also, that like they might have in the door hinge some sort of a thing which just presses, okay, but again the signal would not necessarily be clean at the lowest level, so you want to clean them up. So that signal conditioning is the very first thing that one has to do. Then the other thing which happens at a lower level is sensor calibration. And what this refers to is that how do you relate the number coming out of the A to D converter to the quantity, physical quantity of interest to you. So for example, let's say you are measuring, I don't know, let's say concentration of a molecule in water. And so you're getting your A to D converter is giving some number because you pass some current to the fluid and you are measuring the voltage and you have some reading. What concentration does it correspond to? And the challenge out here is that the calibration values are vary from sensor to sensor for the same type of sensor, and they vary over time. So that leads to the problem. It's a little bit like the problem we faced in crystal oscillators with clocks, which is there were manufacturing issues and then there were issues over time which were a function of environmental condition, aging, all those kind of factors. So what you face is the problem that either you pay for careful calibration by the factory, but even if you do, usually it's not enough, or you have to have some procedure for investing that time and effort to calibrate the sensor while it is deployed. And very loosely speaking, you can employ one of few approaches. One is you have a depth sensor deployed in the field, you bring a costlier, high quality sensor, and then you compare the reading. So that's calibration against a reference sensor. Or you can calibrate by feeding it a known input. So oftentimes sensor chips and all that you buy, they have a self-testing capability. And all that it refers to is that they have a circuitry to feed a known input at a known signal at the input to the sensor so that you can compare the value and then kind of work with it. So the variety of approaches, and many sensors provide built-in self-calibration. So for example, on your phones, you may have noticed that the magnetometer is often goes out of calibration. Any of you encounter this thing where it kind of says move your phone in a 8 thing? No. So the reason that happens is that magnetometers, the technology that sort of these phones use, the sensor has a persistent change when it is exposed to large magnetic fields. So so over time, the sensor's baseline kind of changes, and as the baseline changes, you are still okay for certain kind of tasks where the change in value is what matters. But if the absolute value matters, like you're trying to get the north direction correctly, then you need the sensor to spit out to be well calibrated, and that is where when these things realize that they have gone out of calibration, then they ask you to recalibrate, and that movement of 8 is nothing but a way for they're basically asking you to expose the phone into the different patterns of the Earth's magnetic field, and somehow they make use of that knowledge to then do the calibration. So calibration extremely important, and almost every sensor suffers from it. That is you just have to kind of take into account. Even cameras and all have issues of calibration. There are minor variations across sensors and all. So if you're doing sort of precise sensing and all, that kind of matters quite a bit. In case of cameras, even things like where in the space is camera located, like what is its coordinate system, where is it precisely located, and how is it oriented. So with cameras with such requirement, there are approaches where you project a grid on the 3D world and then kind of compare against it. So every sensor would need some sort of a calibration process for it to work. Chemical sensors usually come in the form of giving you a fluid of known value, and then you test against it to sort of do it. So for example, some of the medical things like those diabetes strip, for example, so they come with a reference strip which you are supposed with which the meter is supposed to be recalibrated once in a while. So sensor calibration and doing it in field at runtime important. Next up, missing sensor data. That's another one which again one faces in real systems quite a bit. Happens for a variety of reasons. Sometimes it's just network outage, sometimes whatever other type of things, maybe the software got tied up doing something else, maybe a firmware update happening, all sort of reasons that there are gaps in the time series, okay? And I would also put in under other such things like misaligned data. Like you may think there are two sensors and they are sampling the same thing, but their clocks were slightly misaligned, and therefore the time series you have are misaligned. So missing sensor data, at the very least, you should know that it is missing. So the challenge that you face is, one faces is that oftentimes the systems don't have a distinction between missing data and a valid null value. So like for example, if I give you an image and there's a region of the image which is just blacked out, was there a black object there, or was it masked, right? Those so oftentimes that distinction may be clear from the context, but oftentimes not. So very important that when one is doing sensing system, this kind of information is also carried through. There is a lot of recent work, as in past 5-10 years, on this missing data problem. So what kind of approaches do you think, if let's say you're analyzing sensor data, let's say time series of physiological data and all, and you see missing data, what could you do with it? What kind of things to repair it or cope with it?
Interpolation.
Okay, so interpolation is certainly one strategy where by looking at both sides you can interpolate. What else?
Copy like a same window from somewhere.
Okay, copying the same window from somewhere else. But you have to decide copying which window.
Either the one before it or after.
Oh, either the one before or after. Okay, fine. That's reasonable heuristic. What else?
Signal redundancy.
What does that mean?
Like having more than one sensor.
Right, okay. So if you have more than one sensor of the same type, you can say, okay, I mean, I got the data from elsewhere. Okay, what else? So building on the redundancy theme, right? I mean, I may not have sensor redundancy, but I may have information redundancy. So to give you an example, I talked about IMUs, accelerometer, gyro, right, and magnetometer. It turns out that you can compute the gyroscope signal from the accelerometer signal. Okay, so I mean basically underlying. Okay, but it will be very much noisier. So it's lower quality, but you could. So there are papers called virtual gyroscope, which are basically saying sort of I can compute the things. This more broadly is called imputation. So the idea is that I may be sampling more dimensions of the signal than are truly there, and therefore by in that interval where I lost this thing, I can kind of use the other data to kind of fill it in. And the reason you want to do this thing is because you have probably designed your software assuming that everything was available. So if I have a sudden outage in one of the channels, and if you continue with your inferencing, which was assuming that everything was nice and clean, then it will behave not very well. So filling in with some reasonable value is a good strategy. So this thing of filling in with one's neighbors, whatever, with the other channels is called imputation. So you have interpolation from past and future, and you have imputation, which is from the other channels. And collectively, by applying all of these things, you can at least have a system that is more graceful in its behavior, basically. So again, almost any sensing system, sort of you would see these outages very commonly for, I mean, this software complexity comes in, sort of bites you. Okay, so after we have done all of that, then comes the task of making the inferences. So, so when we look at sensors, very broadly, you will find that the sensors produce data in one of two forms. There are sensors that generate periodic measurements. So they are basically taking an underlying analog waveform and they are digitizing it and for the moment now let's forget all our compressive sampling and stuff like that. So basically they're producing a time series of measurements. And so for example, let's say they are trying to measure whether the room is whatever dark or lit, then it could be dark, 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 light, 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 kind of they're just giving samples at a periodic interval. And then there are sensors which produce events. And events are basically change of state. So essentially, what we do is we monitor that underlying time series, and whenever we see a change, we send out a change. So instead of saying dark, 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 light, 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 dark, dark, we'll say dark to light transition at time t1, light to dark transition at time t2. So we basically send out reports when a change in the measurement value happens. And there are a couple of reasons to do it. Firstly, many sensors naturally come that way. That is, they are designed to generate an event when a change happens. So for example, a lot of motion detectors and all are like that. They just focus on the change, a motion happening, and then don't send out any reports when there is nothing happening. Another one is this is kind of a reasonable compression strategy, right? If you expect events to happen much rare, the transitions in state to happen rarely, then it's a good compression strategy as well. So kind of at the lowest level, then the output of sort of available sensors fall into these two categories. And now you are trying to make an inference about the state. So as I mentioned earlier, there are kind of two approaches that one can bring to bear into this. One is that somehow I have a model which relates the hidden state to the observed value through some equation. Okay, so I may have some physical model, biological model, which tells me that how that x is equal to some function of the state, and therefore my given the observed, I should just invert the function and to get it. So there's a class of problems which are called as inversion problems, and they're solved in many contexts like earthquakes, atmospheric sensing, all of these things. And basically the way what happens there is that we have good forward models of the physics of the system. So like you'll say an earthquake happens at a certain point in the Earth's crust, and it's basically the sound waves basically. So they are the seismic waves. They're traveling through the Earth crust, and we have good models of them. And then we have observation from an array of sensors on the surface at various points. And then our problem is, given these observations, I want to go back to where the earthquake happened and what was its strength and stuff like that. So these kind of problems which require inverting a physical model are sort of have been done quite a bit, and the forward path is based upon the physics, and kind of the inversion path you basically now are trying to compute the inversion of that. So that's quite common, and in the kind of systems that in IoT community you play around with, a lot of simple stuff falls into that category. But then more common nowadays are methods where we are entirely data driven. Now at a philosophical level, one could say that the physical models were also an outcome of data, right? I mean, physics doesn't happen in a vacuum. Experimental physicists make observations, and then physical laws are discovered that best explain that data, and that's how we come up with kind of the equations which correspond to those physical phenomena. But physics arguably is much easier than the messy world of human spaces with humans and all in it. Okay, so sociology and psychology are messy, partly because we are complex. There are no equations describing behaviors of human societies and all. So, so what has begun to happen now is that we see more sort of a data-driven approach for these things. We have massive amount of data, and through machine learning methods of various types, supervised, unsupervised, reinforcement learning, there's a whole milieu of these methods out there, but common to all of them is that we're exploiting data to discover the underlying rules. So typically, as I mentioned earlier, the algorithms, you don't feed the raw sensor data to them directly. At the very least, you clean them up, condition them, calibrate them and all, but usually you are going to also convert them into features because you know that these features carry the relevant information and therefore are going to be easier to work with. So so somehow you have come up with these features. Some cases, the original data itself is a feature. So now with images and all, it's very common for neural networks to just operate on the features, sorry, on the image. But for other type of signals, like speech signals and all, it is much more common still to feed features which are statistical features in it. So like, for example, for speech, it's often spectral features. For inertial sensor data that we looked at, again, various kind of time domain and spectral features get used. But both these approaches are kind of prevalent, and that whether you operate of some sort of cleaned up, calibrated raw data, or whether you work with features. So from that same deployment that I talked about earlier, what they have done is for a lot of their sensors are event oriented. So like I already said that motion sensors are event oriented. A lot of these things are more naturally can be expressed in terms of events. So what this is basically showing is that a timestamp, the ID of the sensors, so like dustpan, hip, arm, so they probably are instrumented with some sort of inertial sensors, and then you basically end up with either some sort of a tuple which is describing the values being read. So in this particular case, it's an inertial sensor, and you are seeing the numeric values of the A to D converter. And on the other hand, for some of the other things, it was simply an event, like it moved or didn't move. So, so your sensor readings are going to look like that. There's a sort of a set of either a numeric value that you're receiving or kind of a pure category of an event. So hand soap, still, okay, for a lot of IMU type things, these are values. So that's kind of a form of one example of how features might look like. In other systems where there is just a single sensor reading, a single type of sensor. So let's say, for example, you're trying to infer whatever, let's say transport modality, whether you're like sitting, walking, those kind of things from the data on your smartphone, then you might simply take that the 9 degree of freedom vector from the IMU, and that's what you are getting. And it may, in this particular case, these are asynchronous, that is, they are not happening in any periodic manner, but in other cases they might be strictly periodic. So there is a what is raw sensor data could be featured in another context. So again, depends upon some specific systems. Okay, so let's do the following. It's just past 5, so let's take a few minute break, and then we are going to talk further about this.
Do you have time after the class to talk?
Yeah, a little bit. Why? On your project? Okay.
Yeah. I was having just gonna play with that for a while. Yeah, started.
Pardon me?
Will you be in your office tomorrow?
I will be, except I will start. I'll shift them by 30 minutes. So if you can come at like 2:30, 2:35 instead of 2, that would be good.
Okay.
Yeah, I have to meet a faculty candidate.
Can you receive the other
Yeah,
one?
I forgot to bring them today because
Okay,
I
yeah,
left
we
in a
can do
rush.
it. Yeah, we have
But
that.
yeah, I have received it. Yes.
Okay, thank
Yeah.
you.
Yeah, that'd be great. So boring too, hard to track down.
Okay, let's resume. So, um, so in this particular system, the features took this various forms. So next question which comes up is, what generally do the features look like out of the sensor data? And again, there are kind of many different ways of going about doing it. So, and depending upon whether the sensors are event-oriented or spitting out values, you are going to approach it differently. So if the sensors are event-oriented, then features may simply be things like time of occurrence, like time of day or day of week, because they might indicate useful things, because they have these things like day of week and time of day correspond to something about the human life pattern, right? I mean, if someone, if you see a motion sensor trigger on a particular time on a particular day of the week, then you might attribute it to certain kind of activity. So going from absolute value of time to sort of time and likewise location, which have some human world meaning. So location in terms of like things. So I'm trying to make a distinction between kind of the raw value and then mapping that raw value into something which has some higher level semantics. So in case of location, it could be home, work, movie theater, fast food store, those kind of things. So mapping latitude, longitude to something like that. And in case of time, it could be things like time of day, day of the week, was it a vacation day, was it a work day, those kind of things. And then also, if there are events happening, then the duration of those events. So these are just some examples. You could imagine for event-oriented things, there could be other similar ways for you to, for one to think in terms of. So some characteristics. And then if you have discrete sensor values, then again there are sort of common ways of looking at it. So remember, we divided things into windows. So I could now go around looking at these values in many different ways. So one very common way is called bag of sensors. And this analogy out here is something which is used quite a bit in document analysis, where it's called bag of words. So so the analogy goes like the following. So let's say you're trying to analyze documents. So there are a bunch of text files, and you are trying to do something about them. Like, for example, maybe they correspond to reviews of, let's say, movies, and you want to say whether they are positive or negative. Okay, so a very common approach in this setting that happens is that we translate that document into a set of words. So we basically only focus on whether a word occurs or not. Okay, so like whatever particular word, I don't know, London, whether it occurred or not. So we basically reduce and we remove kind of the obvious like articles and kind of words which don't carry any meaning, and we kind of convert it into a set. And that's called a bag of words. And the idea is that we use that as a feature of the document, and we analyze it in terms of that. And of course, you're losing a lot of information. You are losing the information about frequency of the words. You're losing information about the sequence of the word, the way it occurred. But it's one way of characterizing that. You can imagine other ways also, and there are more powerful ways that have emerged in modern systems. But this bag of values is a very common way of looking at it. So essentially, you can just say what are the type of events that occurred, and the next step up is you say what are the type of events, but also their frequencies. So they are kind of both models that exist. Another one is when the event happened, how long was it since the last event? So these are just examples that I'm giving, and this kind of table shows that in a particular window, I may have dustpan happened one time, and a duster or a broom event happened one time, and so on and so forth. So I can basically kind of reduce all that sequence of events into just a frequency-based thing. or sort of the gap, the elapsed time between these events. So that's another way of kind of looking at it. Then, if you have a whole bunch of values, another common way of doing these things is in terms of statistical features over a particular time window. So I can compute, so in this case, it's accelerometer data, and I can compute all sort of things about it. Like usually you might look at like spectral features. What were the strength at different frequencies, or like, for example, how many zero crossings occurred in this thing, or what's the peak minimum to maximum ratio, stuff like that. So all sort of statistical features can be imagined in this context. And then finally, features which relate to kind of higher level things like what was the previous activity that was taking place, or which sensor is most active, things like that. So there are a variety of ways you could think of features, and this is where human engineering and all often sort of comes to play out there. Now, I made a comment earlier that for discrete sensor values, this bag of sensor is one approach, but kind of there are more modern systems also have emerged. And there is a concept which has emerged in recent times, which again started in documents, and it is called the concept of embeddings. I'm sure some of you have heard about it, but the notion of embeddings is the following. So again, if you think of let's say you think of a let's start out with a word, okay, word in a language. So a common way of representing a word in a language might be as an ID number, right? I could just sort the words in our dictionary and just say this word is number I in this dictionary. Or I can represent this thing as a vector, where vector of as many words in the language and then one in the place corresponding to this word, right? There are different ways of kind of representing a word in a language, right? Embedding refers to that there is some, again, I'll use a term, latent space, some hidden space in which these words map, and this space is real valued. So there is some smaller dimensional real valued space, and these words are basically coordinates in there. Okay, so we move away from this discrete thing to this sort of thing. So, and we don't know the dimensionality of that space, but there is something. And if we can map to it, then I have a more compact representation, and perhaps we could do some stuff which is better than that. So I don't have a slide, so I'm just going to draw, but so the way these embedding systems work is the following. Think of them as some sort of an encoder, and they take your discrete value, okay, and they map it. So this is a large, so this is a discrete value vector, okay, or in particular I have a bunch of categories. So this is a vector which is all zeros, and then it is a 1 at the place which corresponds to the category, okay. So I have a sensor which could take one of different categories, and it could be this, or it's a word in a language. And what I'm doing out here is I'm mapping it to a smaller dimensional vector which is real value, okay. So R1 to Rk, and where this k is much smaller than this n. And I could think of some general mathematical function which does this, and typically this encoder is nothing but a fully connected neural network. But you just think of it as, for now, a mathematical function with some parameters. And my goal is to learn a good embedding here, a good way of going from here to the smaller dimensional space. Now, what is a good way? The good way would be that, therefore, there also exists a decoder that can help me recover this. Okay, so so I can get back to the discrete representation. So while I'm describing it in terms of words in the language, but this is kind of more concept. I can feed some categorical structure out here, and then say map it to this small dimensional real valued space. And if I'm doing my job correctly, I should also be able to decode it. And this again is a mathematical function, and again, commonly it is a neural network. And you can think of neural network as just a parameterized function approximator. So it's just learning a function. And I put data into it. So basically what I do is, in case of, again, continuing with my language example, I feed lots of documents to it. Okay, so the way we kind of train it is we feed not just the word of interest, but we also feed the neighboring words that are occurring in the document. Okay, so I feed a vector of vectors out here, and then we go through this path, and our goal is to recover back the word. Okay, so if I'm trying to learn the parameters of the decoder and the encoder such that I'm able to predict the word correctly. And once I have this, then I have this tool to map readings into a smaller space. So that's the concept of embedding. And it turns out this approach has become extremely successful. So it started out with something called word2vec, but now you will see papers essentially along the lines of x2vec, okay, where x is almost anything, because it became successful as a general concept. Now the reason it became successful is that people found that things that you would, that it was, that this space in which I'm embedding, it captures something about the relationship among these words. So, for example, words are often defined by the meaning of a word in a language. It often correlates with what other words occur near them or what they are similar to. So, for example, they found relationships like words with similar meaning cluster together. So, like sort of different synonyms of, let's say, the word king, king, emperor, these kind of things, they occur in the same place. Certain other relationships would hold true. So, like, for example, they found that the distance between man and woman would be the same as distance between king and queen. So some of these relationships would also hold true. So it turns out that fed enough data, some of the relationships that reflect in the real world, documents of the real world, get captured in the relationships out here. And so very commonly nowadays, that what you see, and by the way, the same thing is true for images. You can feed images, and then you reduce that whole image to kind of a vector. And the idea is that somehow in that vector, you're capturing the relevant things. Maybe one of the dimensions out here captures that, does the image have an animal? Another dimension captures whether there are trees in the image, stuff like that. Things which are just presumably corresponding to the real world. So, so these kind of ideas have sort of proven quite successful. So this concept of embedding into vector space of some form from kind of the original data, image, time series, stuff like that, has caught on quite a bit. And so converting it into a vector. So bag of sensors and all is kind of more classical ways of doing things, but nowadays, particularly when neural networks and all, you see this kind of embedding approach being used quite a bit.
Is it so common to do that type of runtime encoding scheme per word?
Well, when you are training these things, yes, and it's actually pretty common. The reason is, since it's a binary vector, you can do operations very easily. You can do distances and stuff like that very easily. Okay, and the thing is, this is pretty sparse vector. So you can, so yes, short answer in the document analysis world is very common, because what's your alternative? If you put word in terms of an index, then it's there is no meaning to that number. It's just an index. So this is pretty common. And you can apply it into our sensing context also, right? I mean,
would you ever combine like this type of one-hot encoding with like a convolutional technique, or would there never be that type of?
No. So this thing usually gets used then when doing distances and stuff like that. So like, for example, very common is that I can take, so let's imagine that I reduce the document to a bag of words, occurrence of the words, right? So I will have a vector where I will have a 1 in those places where the word occurred. So if my language has, let's say, 100,000 words, then I have a vector of 100,000, and then I have a 1 in those places where that word occurred in that document. And now you can define distance between two documents. In terms of distance between those vectors, and very common is a cosine thing. So you can think of these as vectors in space, and you're looking at the cos theta between them. Okay, so those kind of ideas they've been around for a while, and you can apply them in a lot of other settings, right? I mean, I can take my features and do a kind of think of my time series in terms of these. Does it have zero crossing? Does it, right? I mean, I can think of a binary feature vector, for example, and apply these things. Or even if it is non-binary, I can look at the distance, like what's the distance between two time series? Well, normally in E, we simply think in terms of, like do a root mean square between them and all, but what's the distance between when I've reduced the time series into a feature vector? So now you have, so you normalize it and do, of course, some angle between them. That's the reason of it. So these kind of ideas, sort of in classical document processing and all, have been there. Again, they got overtaken by kind of the more sort of reduce the so embedding for the word, and then how do you go from word embedding? So I give you word to vec, okay, and in fact there are standard pre-trained libraries floating around. You can just download them, and they have, essentially it's a gigantic matrix corresponding to a neural network like this. You feed it a word, okay, in the one hot form, and it gives you the embedding for that, okay. And then if you take a document has a whole series of words. So you basically take the embedding of each word in the document and you add them up, you have the embedding for the document, for example. And it turns out, again, a lot of these properties hold true. Same concepts then got picked up in all these other domains also. So a lot of work in sensing and all these sort of things are using similar ideas. That's why I kind of put this X2 there. But deep down, what is happening and is that somehow this latent space, this thing is capturing the useful things about it. And the reason it is capturing useful things, I mean, this is at an intuitive level, is the following. So again, taking the analogy from documents, normally, I mean, in linguistics, basically they try to understand the physics of the language, if I were to put it that way. So in terms of what's the meaning of the word, what's the root and all. A data-driven approach basically says meaning of a word is defined by what else was nearby, its context in the language, right? So if I see a word used next to some other words, then that is saying something about its meaning, because that's, and likewise you can think of in sensory data and all, also these relationships that occur temporal and spatial are saying something about the meaning of that value, that reading, right? So for example, if I always see whatever, door 1 opens, broom motion occurs, door 2 opens, okay, then it's saying something about the relation. And then separately, if I see door 1, same door 1, but a different object, and door 2, then you might say, okay, the broom and that other object have some similar role to play, okay? So somehow, given enough data, those relationships are the ones which are getting captured, okay, in the document. So in the NLP world, natural language processing world, there's been a wholesale shift for the lower layers of natural language processing to these kind of models, moving away from models which were based upon trying to understand the language to one which are entirely data driven. So anyway, so those kind of approaches to features have also emerged as well. But sticking with the more common sort of human engineered features that typically get used, there's a whole laundry list of them, and I've kind of listed a bunch of them out here, but these are kind of things that you may have encountered in your courses and all, but you can imagine, but they're basically kind of various statistical metrics over pieces of data that one might have. And it turns out that a lot of these things have some correspondence with things, and so usually when we are faced with sort of time series data, signal waveforms and all, you kind of compute these things, and that becomes your feature vector. So this is kind of another way of doing this. So this is an example where basically for some particular, I think it's a hip sensor, so they've basically computed a whole bunch of statistical things out here, right? Max, min, mean, blah, 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 blah. Okay, so you basically compute these statistical features, and then that becomes your feature vector. So you go from time series to these values. And a lot of it is based around intuition. Like, for example, the expert will tell you that, like, for example, like the earlier thing I said in code, heart rate variability captures stress. Now, it's coming from medical insights and all, but that's a statistical feature. So between a combination of expert knowledge and then also approaches where you kind of throw all of these to your problem, and then you start pruning away and see which combination does well. So there are sort of ways of going around doing that as well. And not just in time domain, you can do it in spatial domain, and you can do in temporal frequency and spatial frequency. So there are spectral and temporal, and likewise spatial and spatial frequency. So so this is temporal frequency. So like, where is the centroid of my spectra? What's the total energy in the spectrum? What's the entropy? How much is the energy? What are the different coefficients? All those kind of things you can imagine doing, and people do that. So so now at this stage, what you have is kind of a vector for that window, which consists of these different types of features that we have. And in the modern cases, it could simply be an embedding, okay, because it's supposedly capturing a lot of useful information. Okay. Then another issue that arises is fusion of multiple sensors. So remember, even in that running example of deployment in that apartment that I've been using, there are sensors all over, right? All the different things were capturing things about the same activity, right? So when sweeping was happening, it was being picked up by a whole bunch of things, and so on and so forth. So question naturally arises, how do I go around combining these values and combining from different information? And there are very broadly kind of three approaches that occur in this. So one is, so they basically correspond to which layer you are doing the fusion in. So one is data fusion. That is, you basically just say, okay, I have the values from all these accelerometers, let's say, I'm just going to average them, and now going to look at it, okay? So average sensor measurements, maybe you might want to weigh them somehow, like if I'm getting reports from multiple sensors, I may give more weight to a sensor which is known to be higher quality, more trustworthy, whatnot. Another one is you do it at the level of features. So remember, now we had converted those raw readings, the analog waveforms, to feature vectors, and now what I can do is I can just combine all the features together. So different accelerometers, their readings, I reduce them to features, and now I basically create a super feature vector which has features from all the different sensors, and combine them together. And then finally is classifier fusion, which basically says, let different sensors make their own inferences about the activity, and then I'm going to combine their votes, so to say. So maybe 5 out of 7 sensors say it was sweeping, and the other 2 say it was whatever, mopping, and therefore I'm going to say it was sweeping. Okay, so stuff like that. So again, many different ways of doing weighting could be imagined out here. So kind of different ways. So multi-sensor fusion is usually quite important because of reasons of robustness, because sensors fail in different ways, environmental conditions may favor one sensor or the other. So just important to have. So next up then, what are the different approaches for making the inferences that that get used? So again, I'm going to bypass kind of methods that are more physics based and all, mostly because they're kind of obvious in a way. I've probably seen them in some other courses, so I just want to focus on the more data-driven approaches. Again, some of these some of you at least, I'm sure, have seen them, but just wanted for benefit of everyone. So there are variety of approaches to data-driven things which fall under the umbrella of machine learning, which are used, and I've listed them out here. Most common is what is called as supervised learning, but then there is also are things as unsupervised, semi-supervised, active learning, reinforcement learning, and so on and so forth. So but the two most common ones were the first two. So supervised learning, which again falls into these two categories, classification and regression, and then unsupervised learning, where essentially you're trying to look for patterns in the data. Okay, you're conceptually, so trying to cluster the data in some ways. So there are a whole bunch of methods out there, but let's focus on the one which is sort of most commonly encountered, particularly when it comes to sensor processing, and that is the supervised learning. Okay, so most work currently kind of falls into using this category. So the idea now is that I have a training phase of my system, during which I will capture the raw data as well as the label. And by that label, I mean that whatever I was seeking to predict, so if it's a class category, then that somehow I'm capturing that also. Now this is where kind of a challenge which comes into play is that if you think about sensor data, some of it, like images, can be labeled months later by a third party, right? I mean, if I give you an image and it has a person jumping in it, you can always tell a person was jumping by later, and that has advantage that the labeling can be done later. You can farm it out to on Amazon Mechanical Turk or something like that. Yeah.
So like sometimes when you have to like verify if you're like buying something online, you have to like click the squares that are storefront. I don't know. Someone told me that that's actually like Google doing.
That's Google doing labeling. Yeah. I think Google was doing it for the text stuff, and that was to help them build models for their translation system. Okay, I don't think the visual captures are doing that. They are just so annoying. So, yeah, some of them. I mean, particularly the Microsoft website. I don't know if humans can even solve them, but anyway. So. That's a separate story. But by the way, because they're doing it, that's why they also are somewhat error tolerant also. Okay, so you don't have to perfect.
Yeah, I feel like it's still wrong even if you like select all storefronts or whatever.
So images could be done, like you're pointing out, by others later, and I guess certain other things are like that also. But much of sensory data is not like that, right? I mean, if I want to capture the label corresponding to the IMUs on my phone, and I'm trying to learn a model for, like, again, transportation modality, if the person on whom the phone is there, or someone who was watching that person right there and then, or if you happen to capture an image, there's no other way. I mean, just looking at those traces, you can label it later. Okay, not only can someone else not label it, even you would probably not be able to label it. Okay, so a lot of sensory data is hard to label, and therefore a lot of effort has gone into just creating friendly systems for these. Okay, sometimes you do it in supervised setting, like call someone into a room, have cameras there, and then that's when they are kind of doing this training data collection, so that then you can make use of the images to do it. Sometimes someone else tailgates tails the person, so you're going around, and then there is another grad student with the notebook following you, or some poorly paid undergrad doing it. So that's how those studies get done. Okay, they have to be done contemporaneously, right? So that's a challenge. The other thing also is all this stuff has to happen out in some resource-rich setting, right? Training tends to be pretty data-intensive and all. So this high-rate sensor data, you can not just process it at the sensor. It has to be extracted out. So again, some of you who are doing these kind of projects, the challenge you have is that things like Hexaware and all, I mean, while once you have a model, you can run it on that tiny device. But while you are training it, you have to extract all this data, because you're going to train the model on your laptop computer or some even more powerful device. But in any case, the process then is that I'm going to extract the features from it. I've somehow figured out what those features are. Okay, so now I end up with a set of features. Then I'm going to train the model. And what that basically means is I've assumed some structure for the model, and it has some parameters, and I have to learn the best value of those parameters. So it's an optimization problem, right? Because what I have is I have the labels, and I have the features, and I'm trying to learn the parameters of the model which best fit the data. And there are a variety of ways you could go around doing this optimization problem. For simpler models, you may even have exact solutions to do it, like if it's a linear model, something like that. If it's a fancier neural network and all, then lots of parameters, a complicated thing. But we have systems which let you do it. Output of this is the model, which is basically nothing but a parameter file. Remember, the structure is already known, so it's basically a parameter file. And again, simpler models will only have a handful of parameters, but a neural network may have tens of megabytes worth of parameters, because it has gazillions of things to do. But while you are training, you also have to evaluate the model. And what that means is that you have to go back and see how well you are doing on the data you have. And this is where it's very important that you do things appropriately, because if you don't, then your results can be pretty, may not generalize well. So for example, the correct way of doing this thing is that you split your training data that you have into 3 pieces. There is your training set, there is your validation set, and then there is a test set. And you set aside the test set. Okay, and in realistic settings, it's not even going to be given to you. Okay, so don't look at it, not even indirectly, never. Okay, there should be just one test. Okay, and then you take this sort of rest of the data, you split into these 2 parts, and then you are going to train the model on the training component, and you are going to validate it, and you are going to iterate it, and you're probably going to do different splits, like different permutations of the training data, constituting the training and the evaluation set, training and the validation set. And you keep doing it, and at the end, once you are convinced that you have a good model, then you feed it to the test set. More independent the test set, better off you are. So very common mistake is not to have that, then iterate again, right? Oh, my results are not good on test set, let me go back. And that defeats the purpose of the test. Okay, so very important to not optimize for the test set, because again, then you will create a model which only works with that test set, and if a different test set, it will fail. So you don't want a hyper fitting of your model to a particular test, right? So don't teach the model to do the test well. You need a model which does well with other tests also. So very important to make sure that that's done. So now you have the model, and then you are deploying the model. So this is a deployment phase over this kind of where you are actually doing the predictions, you have the new data, again you extract the same features, and you predict the thing out here. And these models can be deployed on the sensor device itself. So nowadays, when people say machine learning on embedded devices or embedded ML or ML at the edge, they're really referring to this, that we are able to deploy the model on resource-constrained devices. We are far away right now of doing learning on the edge devices. It has its needs, it has uses, but at best right now we are at the stage where you do some refinement. Okay, so like for example, your phones, they gradually begin to learn a little bit about your behavior, right? Your particular writing and all, but those are very trivial personalization of the model happening. A true training at the edge, we just don't have the memory resources and all to kind of be able to pull it off.
How about for something like Face ID? Does that use
so Face ID is basically learning features of your face, and that's it, and then it's just doing a vector match. Okay, so it's just not really learning a model in the sense of something which will be then applied elsewhere and all. It's basically reducing the image to a vector and then an embedding of sorts, if you may. So Apple has presumably on trained data. I mean, of course, they would have recruited large number of people to develop that, but they reduce it down to some vector, and they're just doing a vector match on that. Okay. Yeah. So so this is a deployment part, and at this, over the past small number of years, like 1 or 2 years, we have plenty of examples of being able to do this on edge devices, even microcontroller class devices that are present now. Okay, and even some of the tools which operate at this layer have the ability to spit out models which you can deploy on tinier devices. So like TensorFlow, which is used for neural network, now can output stuff which is running on smartphone type devices, and also on certain neural accelerators that exist for like Raspberry class type devices and all. So there's a fair bit of stuff which exists now for taking models and deploying them on, at least I would say, as low-end embedded devices, and I think low-end 32-bit type thing, and type processors and sort of chips. So quite a bit of stuff is here. MATLAB, for example, has the ability to spit out C code if you have the appropriate sort of add-on to MATLAB. So those are other ways of kind of doing things. Also, there are special libraries floating around, and also there's a lot could be done. And by the way, this is for the heavy duty stuff. If you have a linear model or something like that, those are obviously very compact and easily deployable. So this whole supervised learning nowadays, even, I mean, we hear that how things changed when it came to image and speech and these kind of things, but the same concept is also playing out for sensory data also. So even these things like accelerometer data and other type of sensor data, lots and lots of work where neural networks are being used. And I'll talk about more on tomorrow, but basically the attractive part behind neural network is that at the input layer, oftentimes you can just take the raw data or an embedding of the raw data and kind of work with that. And the rest of the stuff is kind of very generic. And once you have a trained model, you just feed it and it sort of works. But in many cases, still we do feed the features. So the other attractive part is that these models do these kind of things are doing pretty well. So while even though we may not have any physical understanding of them and all, we don't have a reason why it outputs a particular decision and all, whereas in a simple model like a linear classifier or something, you might be able to, or a decision tree, which is very intuitive to look at and say, what is it doing? But the results here are so much better that they have begun to catch on quite a bit. So a lot of stuff basically uses neural networks even on the sensory side of things. So it started out with, I mean, neural networks, as I'm sure you know, are not new. There have been many eras of neural networks going all the way back to 1940s and 50s, where there were always kind of this more kind of standard computers, the von Neumann architecture and all, and then there was also this area called cybernetics, and there were sort of people who were sort of fan of that, and they always were fascinated by the idea of like, could we create computers which are kind of like human brain in some regard, and the human brain is this network of neurons, so that was kind of their driving paradigm. That is, could I create machines which are more inspired by that. So they literally took a simple model of a neuron. Kind of the simple version of what happens in the human brain is that the neurons get signals from other neurons, and they are weighted, and the summation is then subject to some sort of nonlinearity, and then the output happens. A key thing about human brain is that the neurons operate, the information coming and going out of neurons are in terms of spike trains. So the information is encoded in the rate at which the spikes occur on a signal. But other than that, conceptually what they're doing is that I have a vector, and I'm going to take a linear sum of it, and then I'm going to apply a nonlinear function to it, and that's my neuron. Okay, and it turns out that if you create, so firstly, if all you have is a single neuron, obviously that's all it can do. But there are results showing that if you have two layers of this, that is, I feed inputs, and then I take this output and feed it to another layer, and I'm allowed to have arbitrary number of neurons, then I can do any arbitrary function. So it's, in the sense, anything that is computable could be done using structures made of this neuron. So in that sense, it is what you would call as Turing complete. That is, anything which is computable can be done using a machine built using this structure. Just like in your digital courses, you're taught that we can do any combinational function with two input NAND gates, and therefore I can compute any function that can be computed. Kind of same thing holds true out here, that anything that is computable can be done using a sufficiently rich structure of these nodes. Many activation functions, forms of activation functions, but the key thing is that for us to be able to train these things, it's good to have this G to be differentiable, or even twice differentiable. But on the other hand, if it is a very complicated function, then it becomes tricky to compute. It becomes more intense. So if it was linear or linear-like, then, or simple to compute, then it's better. So there's always this tension between keeping G simple, but yet have nice mathematical properties so that it's differentiable. So a lot of things that happened have been a consequence of this. So the way you train a model, very intuitively, so one way you kind of solve some optimization problem, but intuitively it's simply, I feed an input, I see how much error, what result came out of the output, I compare it against my label, and then translate that into an error, and I say if there is error, then I'm going to modify the weights appropriately, modify the parameters appropriately, so that there is kind of a good match. That's basically the act of training, very hand-wavy fashion. So the optimization basically says, what's the value of parameters of the model which best fits my training data to the labels, okay? And the same thing gets applied out here. If I have a network of these neurons, then each neuron, the parameters of the neuron are these thetas. So if I have large number of n neurons in the system, then I have n times these many weights, and that's the parameter of a neural network, parameters of a neural network, and that's what you will be training. So we'll continue this next time. Also, next week, so just a reminder, there is no class on Tuesday, and on Thursday, my postdoc Luis is going to talk about security. So it's back to kind of OS and firmware aspects of embedded systems, but really from the perspective of what kind of security vulnerabilities they present and how to watch out for them. Okay, so see you tomorrow.